homogeneous, so I'm just going to say homo there. And so this is the equation mx double dot, and I'll put a sub h here so we know it's the homogeneous solution, plus bx dot h plus kxh equals 0. And then we just need a particular solution to the inhomogeneous, so the one we have up here. And then the general solution is just going to be the sum of those. So you take the general homogeneous solution plus your particular inhomogeneous solution. That's a general solution for the actual full equation. So I'll leave it to a differential equation class to justify why that's the case. But this is what's going to outline our approach to this problem. And we have the homogeneous solution already from Monday. That's the damped harmonic oscillator. So if you go back to those notes, it's going to be that e to the minus beta t, and then some of those exponentials inside parentheses here. So we're just going to focus on the particular solution today. If you weren't here Monday, then you want to grab some of these notes because those are going to be important. So we're going to focus on the particular solution. Okay, and specifically, we're going to do a special case today, a very important case, and we're going to say that f of t. So let's do a couple things here. So first, I'm going to say it's only oscillating at a particular frequency, so I'm going to say it's f naught cosine omega t. And the reason why, so how do I put this? It may seem like we're looking at an unnecessarily specific case, right? Because there's going to be plenty of problems where your driving frequency isn't a simple cosine. But what you'll learn, I don't know if they do it in DiffyQ, your textbook certainly has a chapter on this, but if you have any, say, function of time, you can do what's called a Fourier series, so you can write this as a sum of sines and cosines, and then you just have a bunch of equations where this is your driving force. So if you can do this special case, then you basically have all the cases done. So that's why we're looking here. The other thing we're going to do, and we did the same thing on Monday, is we're going to divide through by n to simplify this and define and say new variables. So what we're going to have is x double dot plus 2 beta x dot plus omega naught squared x equals, and then I'm just going to call this f naught cosine t, where I've just divided the big F by m. Okay, so, and you can infer what the new, like beta, for example, you can infer that 2 beta equals b over m, etc. Okay. Now, the trick to doing this, so this differential equation is actually, if you approach it as it's written, it can be deceptively difficult. But do you remember kind of one of the lessons we learned Monday, or at least I stated maybe? Sometimes sines and cosines can be a pain to work with, so complex exponentials. So what we're going to do is we're going to generalize this to the complex plane. So generalize is maybe a weird word to use here, but I can't think of a better one. Okay, and basically what that means is this cosine omega t goes to an e to the I omega t. So we'll say okay, I'll let our solutions, x of t, that variable, go to, say, z of t. And it's understood that at the end of the day, we have to take a real part. So I'll say, can people see if I write this slow? You guys in the back?
Yeah.
Yeah? Okay. So I'm going to say x of t, at the end of the day, is going to be the real part of z. Because at the end of the day, our solutions have to be real. The only reason why we're putting in these imaginary numbers is it makes life easier on us. Okay, so then we could rewrite this as delta dot plus 2 beta z dot plus omega naught squared z equals f naught e to the I omega t. And so this point is where we're gonna do something specific here. And to motivate, basically we're gonna assume a form of solution, right? And so you can imagine, suppose you have a niece or nephew or whatever on a swing and you start pushing them at some frequency, right? So suppose you push them every 1 second, you give a push. Then when you first start, you're gonna kind of be out of sync, right? They're sitting still, you push, you give them that initial push, they start going. You push again in a second, they may not have come all the way back, right? So you're gonna be a little out of sync. But if you give it long enough, you'll be in sync, and then every time you give them a push, they'll come back just in time for you to give them another push. And so that's what we call the steady state solution. So eventually, this solution Z will oscillate at the same frequency as of our driving force. All the other frequencies should eventually dampen out. And so we're going to assume steady state solution. And we're going to say this is going to oscillate at, say, Z naught e to the I omega t. Namely, it oscillates at the same frequency as our driving force. And in the future, when you hear somebody say the steady state solution, that's all they mean is that it's the solution that's oscillating at your driving frequency. So you've waited long enough for all the other frequencies to dampen. Okay. So now we have differential equation, we have our assumed solution. What's our next step?
Take it back to a real number?
Not quite. We'll do that eventually, yeah. Yeah, plug it in. We got to figure out what this Z naught is and all sorts of stuff. In fact, I may have introduced a different, I want to make sure I'm using the same variables as here. Okay, so just for my own sanity, because in the notes we have this as a C. It doesn't matter, it's just a symbol, but I'm going to call this a C. That way I can look back at the notes when we're halfway through. Okay, so yeah, we just take this expression and plug it in here. And so when we take a second derivative, we're going to get a minus omega squared. First derivative, we're going to get an I omega. And so what we end up getting is omega squared times z plus 2I beta omega times z plus omega naught squared times z equals f naught e to the I omega t. And then what we can do, this z has this e to the I omega t in it. So I'm just going to divide everything through. I'm going to get that time dependence out of there. So what we're going to end up getting is minus omega squared plus 2I beta omega naught squared times our amplitude equals f naught.